In this session of chemical bonding, we're going to talk about the domain and the molecular geometry. Now, this is called the electron domain geometry. Now, you know that geometry, we're just talking about the shape of an element. Now, what is this electron domain geometry? So, one thing that you should understand is that when we're talking about electron domain geometry, we're just referring to, the arrangement of electron groups. It can be either be bonding or non-bonding pairs around the central atom. So what am I saying? Arrangement of electron groups now this can be bonding or non-bonding, okay, around a central atom. Okay, then another term that we need to understand is molecular geometry. Now, when we're talking about molecular geometry, we're just talking about the arrangement of atoms in space. Okay, so in simpler terms, I can just say the shape of that molecule. Okay, let's look at some of the examples. Let's say you have a structure, this is us. Then we have a central atom here. Okay, so you're able to see that these ones are in a straight line. So therefore, the electron domain geometry, how many bonding pairs does it have? It has 1 and 2, and these ones are in a straight line. So therefore, the electron geometry for this one will just be linear. Then you look at the shape as well. The shape is also linear. Okay, common examples that you can talk about for this one is carbon dioxide. And how do we represent carbon dioxide? Our central atom will be the carbon bonded to oxygen, like that. This is a linear structure. Okay, what if you also have another structure? Let's say that is our central atom. Then let's say it's bonded like that with another one down. Okay, so this one will be called the trigonal planar. Okay, so you're able to see that it forms something like a triangle. Okay, so that is the the electron domain. So the shape itself is also trigonal planar. Okay, so the common example that you can give on this one is your boron trifluoride. So let's say boron is our central atom. This boron is connected to F. It's connected to F, and it's also connected to another F. You can either put it down or up. So let me put it up. So this kind of an arrangement, okay, is called a trigonal planar. Now you can also have another arrangement of a trigonal planar. Let's say this, let's say you have this is our central atom connected to these two things. Then we have lone pairs here. Okay, Lone pairs are those, just electrons that are not bonded to anything. So these ones are bonded to A, but lone pairs, these ones, they're not bonded to anything. So this one is also a trigonal planar. Okay, how? Because it's connected to three things. We said the electron domain is just, the electron groups, both bonding and non-bonding. These ones are bonding, and the lone pairs are non-bonding. So those are specific regions where you're going to find, like, there's a high concentration of electrons. That's why we call them electron domain. Okay, so now because it has three, it will be a trigonal planar. But now, what will be the molecular, the molecular geometry, the shape? You're able to see that mostly the shape for this one tends to bend. Okay, so the way it's going to be is, okay, so the way it's going to be is, your x will go like that and your x will go like that. So what causes this is that your lone pair of electrons, they tend to, to repel, the bonding electrons. So because of that, you find that the shape becomes bent. Okay, so an example of, a common one that we know about is, water. So the molecular geometry for this compound is, it's a bent shape. Okay, the shape, if you look at the shape, is just a bent shape. Then I've said the common example that we can give is water. Okay, so this is our oxygen. It's connected to hydrogen, connected to another hydrogen. But now our oxygen has two lone pairs of electrons. Okay, so now what are we talking about? You're able to see that for oxygen to attain stability, okay, so you've got these four electrons which are lone pairs. Okay, then the other two are bonded to, they're being, there's a covalent bond between oxygen and the hydrogen on both sides. So you tend to have two lone pairs which are not bonded to anything. So because of that, those lone pairs will tend now to repel the bonding electrons. Okay, because you know that electrons are negatively charged, therefore they're able to repel the other electrons which are bonding, hence causing that shape. Okay, so very, very important for you to understand. Okay, now that we've talked about, a trigonal planar, let's talk about something that is connected to four things. Okay, allow me to use the same step, the same place, but I'm just going to squeeze everything. Let's say you've got x, you've got x, you've got another x, and you've got another x. Then let's say this is your central atom. Now your central atom is connected to all of them, this side, the one down, and the one up. Okay, so what kind of a shape is it going to be? Okay, you're able to see that it's connected to four things. So this one, the shape, the electron domain, because it's connected to four things, it will be called a tetrahedral. Okay, then what is the shape? The shape is still tetrahedral. Okay, the shape is still tetrahedral. Now a common example that we can give for this one is which example can we give for a tetrahedral structure? Let's say methane. Methane is CH4. So our CH4, so carbon will be our central atom, this carbon is bonded to 4 hydrogens. Okay, this side, that side, that side, and that side, and down. So that is methane, CH3. So CH4 actually. So that would be the tetrahedral structure. Now, let's say instead of all of them being bonded, let's say we have a lone pair here. What are we going to have? Okay, so I'm saying this is our A. This A is connected to, you know, these elements. Then on top, this A has lone pairs like that. Okay, so what will be the domain geometry? You're still able to see that it's still connected to 4 things. So this will still be called a tetrahedral. Then if you look at the shape, okay, so the shape for this molecule will be trigonal pyramidal. Okay, okay, so it tends to make something like, you know, a pyramid. So that so it will be called a trigonal pyramidal. So now a common example that you can give for this one is ammonia. Okay, now ammonia, if you look at the structure, ammonia is NH3. If you look at the structure of ammonia, yes, and nitrogen is our central atom. You know, this nitrogen is connected to H, is connected to H, it's also connected to another H. But on top of that, this nitrogen has, you know, lone pairs like that. So this will be the trigonal pyramidal. Okay, so it has one non-bonding pair, you know, like that. So this is a tetrahedral structure. Now let's talk about another one. Let's say, how can we manipulate this one? Let's say instead of just having one lone pair, let's say we have 2. Let's say this is X, this is X, and these ones are connected to our central atom, which is A. Now this A has 2 lone pairs instead of 1, so it has 2 lone pairs. So what would be the electron domain geometry? So you're able to see that how many regions are going to have electrons? 1, 2, 3, and 4. So this is still tetrahedral. Okay, so this is still tetrahedral. But now what would be you know, the shape? So you're able to see that this shape is it will be bent. Okay, it will be bent because it just looks like the same with water. So this will be a bent structure. Okay, to be a bent structure like that. So I think I've just repeated what I just talked about. Okay, yes, now let's talk about something else. Let's say instead of being connected to 4 things, let's say our A is connected to 5 things. So this is A, our central atom. Our A is connected to 5 things. 1, 2, let me say 3, 4, 5. Okay, okay, So what would be this structure? So you're able to see that you can make a pyramid from here to there, okay? Okay, that's a pyramid on top, okay? On top you have a pyramid, even down you're going to have a pyramid like that. So because you've got two pyramids, one on top and one down, so this one, the electron domain, how many things is it connected to? It's connected to 5 things. So this one will be called, because it has two triangles, okay, one down, one up, and one up and one down. So this one will be called a trigonal, okay, trigonal bipyramidal. Trigonal bipyramidal. Same with the molecular, the molecular geometry. The shape is also trigonal bipyramidal. Okay, so you have to know that one. It's one of the most important that you need to understand. Okay, so let's talk about another example. Let's say now, how can we manipulate this one? Let's say instead of it having, let's say here where there is x on top, I'll just use the same one. Let's say we're here where there is x here. Instead, let's put a lone pair. So when you put a lone pair, when you put lone pairs here, this one will be called a seesaw. Okay, so it will be called a seesaw. Okay, so even the molecular geometry is a seesaw. Okay, so that is a seesaw. The common one that we can talk about is, which one? Like we can talk about sulfur tetrafluoride. Now, sulfur tetrafluoride is just SF4. Okay, so your sulfur is the middle atom, or let me say your sulfur is the central atom. Okay, so let's put sulfur on. Let's say this is sulfur. Okay, let me just use a different color. So let's say this is our sulfur. Okay, this is connected to F, 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 and another F. But now here we have a lone pair like that. Okay, so that would be a seesaw. Then let's say now it has two lone pairs. Instead of one, let's say it has two lone pairs. What is it going to be called? Let's say it has two lone pairs like that. So how many things is it connected to in terms of the electron domain? You're able to see that it's still connected to 4 things. There are 4 things, but it has two. It has it has lone pairs. So this one is still a seesaw. Okay, but if we look at the shape, so the shape of this one, it will be like rather different a bit. Okay, so it will be rather different. Actually, let me say we wrap this X, okay, to make it interesting. So if it's like that, then what we have is a T shape. So it's It's like that. It's like a T. So the shape is a T shape. Okay. So an example that you can talk about is chlorine trifluoride. Now, chlorine trifluoride. Okay. Now let's if we draw this one, how is it going to be? We are saying this is your chlorine, your central atom connected to fluorine, connected to another fluorine, and connected to another fluorine down. Okay, connected to another fluorine, then they are, lone pairs like that. Okay, so that is another shape. Then we can also talk about another one. How can we manipulate this one? Okay, I think we've exhausted all our chances. Let's say now this A is connected to, let's say it's connected to 5 things. No, we've talked about 5 things. Let's now say it's connected to 6 things. Okay, our central atom, which is A in this case is connected to 1, 2, 3, 4, 5, 6. Okay, so let's say these are our elements. These are our elements. Okay, so those are our elements. So this one, maybe even just the way I've drawn it, but in terms of because it's connected to 5 things. Okay, let me put it like that. Let me say this is our okay, let me draw it nicely. So if we say this, we say that. Okay, this, that. Okay, 6 things. Okay, so let's say these are our elements connected to the central atoms or to a central atom. Now so you're able to see that if we are going to join these ones, you are going to have a square down, like a square like that. Then there's a high chance that again you're going to make a pyramid. Okay, so there'll be a pyramid on top and also another pyramid down. Okay, another pyramid down like that. So because the base is a square, so this one, it will be called a square by pyramido. Okay, so it will be called a square by pyramido. By to mean two, right? 2 pyramids, one up and one down. Okay, so the molecular geometry will still be square by pyramido. Okay, so you must know that one. Very, very important for you to know. Okay, then what if we say, let's talk about the last common one, xenon. Okay, so allow me to rub what I've just written. Okay, So if we're going to talk about, xenon, let me say this is our central atom connected to, let's say, 4 things. Okay, this is X, this is X, this is X, this is X. Then it's connected, it has 2 lone pairs. Okay, so because it has 2 lone pairs, and you look at it's still connected to 8 things. Okay, so this, it will still be a square bipyramidal. Okay, a square bipyramidal is also called an octahedral. Okay, an octahedral. Okay, but now if you look at the structure itself, this one is the shape is square planar. Okay, the best example that we've been able to state is xenon. In this case, we're talking about xenon tetrafluoride. Okay, so XeF4, like that. Okay, so your xenon is xenon. You know that xenon itself has it has a stable, it's one of the noble gases, very stable configuration. Okay, so that will be your structure. So you have to know all these ones for you to be good. Okay, so this is where we end for today. See you in the next session.